Okay, let's have a look at calculating the enthalpy of a reaction using what we know as the standard enthalpy of formation for the components of that reaction. Now to do that, we need to bear in mind conservation of energy. So at the initial part of our reaction, the total energy or total heat for the system should always equal the total heat for the products. Now if we bear this in mind, we can actually calculate our heat of enthalpy for a particular reaction. And we do this by getting the final energy component or final enthalpy for our reaction minus the initial enthalpy for that reaction. And depending on which of these two values is greater, will tell us whether we have an exothermic or endothermic reaction for that particular reaction. Now we see this commonly written as the change in enthalpy for a reaction is always equal to the total enthalpy for the products minus the total enthalpy for the reactants. We have some standard conditions that we use for the standard enthalpy of formation for those components. Our frame of reference is that we always have this at 298 K and 1 atmosphere. And typically we'll also see a molar component in there as well. So how can we use this system? Well, first of all, and most obviously, we can calculate the heat of a reaction, or the enthalpy for a reaction. Secondly, we can actually calculate the heat of formation for one single component within that reaction. Let's have a look at both examples. So first of all, let's calculate the heat of reaction. And I've got an example here of aluminium reacting with ammonium perchlorate to give us aluminium oxide plus aluminium chloride plus nitric oxide plus our water. Now the information that we need is the heat of formation for our products and reactants. So our ammonium perchlorate, to form ammonium perchlorate from its initial atoms or initial reactants is 295 kilojoules per mole. So it's actually an exothermic reaction. Similarly, our aluminium oxide, exothermic reaction, minus 1676 kilojoules per mole to form our aluminium oxide from its components. Our aluminium chloride, minus 704 kilojoules per mole, once again exothermic. Our nitric oxide, it actually takes energy, so it's an endothermic reaction, and takes 90 kilojoules per mole to form it. Our water, to form from hydrogen and oxygen, minus 242 kilojoules per mole, once again exothermic. And our aluminium in solid form takes 0 kilojoules. So what we say is we have to have a frame of reference, and our frame of reference is that any element in its elemental form at 298 K, 1 atmosphere, will always be 0 kilojoules per mole to form. And a nice little example of this is we say that our frame of reference is iodine in its solid form. If we want to make it into a gaseous form, it's going to take 64 kilojoules per mole to convert this. So this is our frame of reference and is 0 kilojoules per mole to form, but to form the gaseous form is going to take energy to do it. So if we use our equation before, the heat of reaction for this particular reaction will be the total heat for the products minus the total heat of reactants. So we have, for our products, we have 1 mole of our aluminium oxide, 1 times the minus 1676, plus 1 mole of our aluminium chloride, so minus 704, plus 3 moles of our nitric oxide, so 3 times plus 90, plus 6 moles of our water from here, so plus 6 times minus 242. That's all of our products. And if we add that number up, that's the total heat for our products. If we have a look at our reactants, we've got our aluminium, we said was 0, so it's 3 times 0, plus 3 moles of our ammonium chlorate, so 3 times the minus 295. And if we do this calculation, our total will be minus 2677 kilojoules. Because we've got the negative value in there, this reaction is going to be an exothermic reaction. In our second example, we're going to have the reaction of glucose plus oxygen. If we combust the glucose, we get 6 moles of carbon dioxide formed plus 6 moles of water formed, and our heat of reaction for this one is minus 2,800 kilojoules. So once again, an exothermic reaction, but we're asked to find the heat of formation for our glucose. So our table says that we have our heat of formation of carbon dioxide per mole is minus 393.5 kilojoules per mole. Water per mole of formation is minus 285.8 kilojoules per mole. Oxygen, because it's in its elemental form at 298 Kelvin and 1 atmosphere, will be 0. And our unknown is our formation of glucose. So we're asked to calculate that. And I'm going to give it the term X for the moment. So once again, we have our equation. Heat of reaction will equal the total heat for the products minus the total heat for the reactants. So minus 2,800, which we've been given from this particular equation up here. So minus 2,800 is equal to, this is our products, 6 moles of carbon dioxide, so 6 times the minus 393.5, plus 6 times the water, which is minus 285.8. That's our total heat for our products, minus 6 times our oxygen, once again elemental form, so 0 kilojoules per mole to form, and 1 lot of our glucose there, which we've said is X. And if we solve for X, our heat of formation for glucose is minus 1,276 kilojoules per mole. So what we're saying is to form glucose from its components is going to, from its components, if we make it from carbon, hydrogen and oxygen, it's an exothermic process, and we will create 1,276 kilojoules